Um, yeah, let me start with some notation. So A denotes a unital sister algebra, and the hypothesis of unital, it's not necessary all the way across, but let's just assume it to keep things simple. And then I denote by GL0A the connected component of the identity in the group of invertibles of A. And the way I think about it, the way it enters the arguments of the theorems and so on, is always as the group generated by the range of the exponential map. So, and also you could even take this as your definition in the non-unital case. So similarly, we look at unitaries. So U0 of A, I denote by that the connected component of the identity in the group of unitaries. And I always, almost always like to think about it in terms of the range of the exponential map. So generated by exponentials. Okay, so then we will be looking at, we'll be mostly interested in the commutator subgroups. So I denote, I put a D for derived, derived group of GL0A. That will be the subgroup generated by the commutators of the invertibles, and a typo in this case, for the unitaries, well, it will be the commutator subgroup generated by commutators of unitaries. So the second line. Okay. So every now and then, some actual commutators come up. So let me actually give the notation. For multiplicative commutators, I use parentheses. And for, well, I guess ring commutators, I'll use brackets. And I also applied this notation to sets. So when I apply it to sets, I really mean generated by commutators of elements taken from the sets. So X brackets Y will be the linear span of the commutators, or the group generated by. I can clarify that when it comes up. Okay, right. So, okay. So let's talk a little bit about the exponential map, which I already mentioned. So I just want to recall briefly this consequence of the Campbell-Baker-Hausdorff-Dynkin formula. So here, A could be a Banach algebra. And basically, what this theorem I stated here is saying is that if I multiply exponentials whose norms are small enough, then again, I can express that as a single exponential. And I have some, the actual formula tells you how the exponent of the new exponential exactly looks like, but it's a relatively complicated formula. It's a sum of iterated commutators, But the first two terms in that long sum are the X and the Y that we used, and all of the other terms, we can gather them into a commutator with X and a commutator with Y, basically. So this is a corollary of that formula. And we do need to be working in a relatively small neighborhood of the identity. Now, if we were working with self-adjoint times the imaginary unit, then again, it is useful to know that A and B are skew adjoint as well. Okay, right. So this should be familiar. Okay. So one more slide about the exponential map. So this is a result that does the opposite of the formula that I showed. I have the exponential of a sum, and I want to break it up into a product of two exponentials. So this is not a result that is very well known, I think, but it will be quite useful for us, or it has been for me. So basically what it says is that now, in this case, I don't have a very clear understanding. We don't really get a very clear formula for epsilon, but we know that when we're close enough to the identity, or the exponents are close enough to 0, then it is possible to break up an exponential of a sum into conjugates of x and y. And R and S, there's some understanding of the formulas for R and S. They're given by series of iterated Lie brackets, you know. So, so this theorem was conjectured by Thomson in the 80s, and then Rouvière, in a conference, he presented the conjecture, Thomson. Rouvière pointed out that using some kind of fancy manipulations of the Campbell-Baker-Hausdorff formula that go by this name of Kashiwara-Byrne equations, one could prove it. So then eventually Rouvière published this like 20 years later, and it's possible to adapt it to Banach algebras. So this is a theorem for Banach algebras. Okay. So here, for example, I show a corollary. Okay, so let's say I have an exponential of a sum. Then it's always commutator equivalent to the product of the exponentials. So typically the way this corollary is handled, people use the so-called Trotter formula. But the Trotter formula will give you a limit of, so it will tell you that e to the x plus y and e to the x times e to the y differ by something in the closure of the commutators. But this is an improvement in that I get a finite product. And anyway, the way this is a corollary is, well, if x and y are very small in norm, then it's a direct corollary, because I can rearrange the terms on the right side to get e to the x and e to the y up to commutators. And if x and y are not very small, I can first divide them by n and raise to the n. I take like an nth root. I work in a small neighborhood of the identity. I apply this and I raise again. So it's a pretty handy result. Now, I will not make it explicit how this comes up in the theorems that follow, but it is just a little machine that one uses all the time. Okay, so let me just mention quickly a theorem of mine when I was looking. So the way that this work came about is that I first started working on a number of questions relating to Lie ideals of sister algebras. Okay, commutators of the kind x y minus yx. And then I understood how those things could be used to prove theorems about multiplicative commutators. So there's these two sets of theorems. So in the slides, I will present the kind of additive version of the theorem, or ring version, and then the group version. Okay. So my first theorem in this slide is it's about ordinary commutators. And what it says is that if you have a unital sister algebra without one-dimensional representations, then the linear span of the commutators agrees with the linear span of the square zero elements. This is not true for arbitrary algebras. This is the proof uses functional calculus. I don't even know if it's true for Banach algebras. But there are counterexamples just in the purely algebraic context. So I pose this question here: do we always have this without unital and without one-dimensional representations? So yeah, so that's so here it's important that there's no closure. If we take closure, then the theorem is true. So these two sets have the same closure. Okay. But the question is without closure. Okay, now let's move on to the multiplicative setting. Basically, using the two theorems that I showed you before for breaking up exponentials and also mixing them together, then one can prove the first part of the theorem. It's not difficult to show that the exponentials of commutators are generating set for the exponentials for the commutator subgroup of the invertibles, and similarly for unitaries. But then I have to make sure that my commutator is self-adjoint. So this type of commutator here is self-adjoint. So I mean skew adjoint, you know. So with the I in front. Okay. Now the second part of the theorem, though, the one about not one-dimensional representations, this uses the theorem, the additive theorem, and so it could very well be that part 3 and part 4 are always true. But at the moment, seems well.
Leonel, there's a question in the chat.
Yeah.
Jonathan asks, is A an arbitrary C-star algebra in the question?
Yes, I mean, let's assume unital throughout, unless I clarify it. But yeah, it's just any C-star algebra. So yeah, without one-dimensional representations, then we get 3 and 4, where I can use square zero elements. And for example, a corollary is that in this second situation, the groups are perfect. So in other words, if I take again commutator subgroup, I don't get anything, you know, I get the same group again. I do exploit these square zero generators for that. Okay. So, yeah. All right, so one. Okay, so now let's talk a little bit about a history of questions relating to these groups. Okay, so the theorem of Cadison from the 50s says that he investigated the group of the invertible group and the group of unitaries, and he proved topological simplicity modulo the center, meaning that if I take, say, the group of unitaries and divide by the center, then it's a simple group. Now, sorry, it has no closed normal subgroups. So that's the question of topological simplicity, meaning no non-trivial closed normal subgroups. And modulo the center means that after we divide by the center, that's the group that is topologically simple. So a number of people look into these questions before, and Cadison himself raised the question whether algebraic simplicity was true. So Kaplansky, and it is a little bit tricky to keep track of the history there. So so eventually Kaplansky, I think, handled the group of invertibles, and the ARP also the group of unitaries, and this took a little bit of time. So the theorem of de la ARP is a late 70s theorem. So, and that dealt with the final case, which was that the unitaries of a factor, of a simple factor, form a simple group, algebraically simple, once you divide by the center. Okay. Then de la ARP and Scandalis moved over to the C-star algebra setting. And they proved that if you have a simple AF C-star algebra, then both these groups, the commutator subgroups, are simple modulo of the center. And in this case, algebraic simplicity. And this is a result from early 80s. So this question then was kind of investigated. I mean, Thompson has a paper on some AH algebras, Elliott and Rotterdam, Ping and Efren Ruiz, and also consider topological simplicity, or I think in their case, it's just topological simplicity, assuming a number of properties. So through my work on Lie ideals and some basing it on some earlier work of Herstein on Lie ideals of rings, I came to see a number of techniques to approach these problems that differ from from the methods that were used in this list, in that I don't need to assume somewhat much of a matrix structure in the algebra. Okay, so I will start with the question of what are the closed normal subgroups of the invertibles or of the unitaries. This is a question that one can answer completely, in a sense. Okay. So again, we don't need to assume any type of structure like existence of projections or stability or anything like that. Okay, but as before, I want to show you the additive theorem, the multiplicative theorem, and the truth is that the bridge is never immediate. Okay, but it does use the properties of the exponential map. Basically, we use the properties of the exponential map. So, okay, so what's the first theorem? It says that if I have, it describes for me the closed Lie ideals of a C-star algebra. So by a Lie ideal, I mean always a vector subspace that is when I take commutators with the algebra, well, it's contained in itself, and this is a closed Lie ideal. Okay, then the theorem that I present to you of Breschar, Kissing, and Schulman, you need to spend a little bit of time looking at it to understand that this theorem, in a sense, describes for you all closed Lie ideals. So, because what it says is that there is a closed, in the sense that it pegs them to close two-sided ideals. And if you understand the lattice of close two-sided ideals, then you see how closed Lie ideals emerge from that. Sorry, there is a question or two? Oh, I can't hear.
What a Lie ideal is?
Oh yes, just a vector subspace that when I take commutators of anything in the vector subspace with the algebra, I get something in the vector subspace. So for example, the span of the commutators is certainly a Lie ideal. And the linear span of the projections of a C-star algebra is a Lie ideal. It's not immediate, but this is true. And
so the definition is in the brackets of the theorem.
Yes, that's the definition. And then I assume it's closed as a norm closed. Yeah. So this theorem, if you spend a little bit of time with it, you basically know that if you understand your lattice of close two-sided ideals, you know how the Lie ideals come out of those. Yeah.
You're being asked if the theorem of Breschar, Kissing, and Schulman is true for Bonic algebras.
That is a question. That's not, no. I mean, I thought about it at the time. I don't know if it is. It may be that it's not true, but and that is none. I don't remember. I do know that the proof uses, basically you use approximately central units. So for ideals, so you need to know that ideals have approximately central units, and you use that the C-star algebras are semi-prime rings. So these are the two ingredients. If you have a semi-prime ring and all its ideals have approximately central units, approximate units, then you're in business. I think that then the proof goes through. So, okay. So the second theorem now is the multiplicative version. We use properties of the exponential map in a not so obvious way. And we get that if you have any closed normal subgroup of the unitary group, then when you take multiplicative commutators with the whole group and take the closure of that, it's the same as taking multiplicative commutators of unitaries arising from an ideal I and taking the closure. And this, and by unitaries arising from an ideal, I mean in the unitization of the ideal. And again, it takes a little bit of time, but this theorem essentially describes for you all closed normal subgroups. Okay. And I should mention also that in the case of closed norm, if you have a closed subnormal subgroup, so if you have a closed subgroup that there's a chain of normal subgroups in between all the way to the total group, that's subnormal. Then in the case of sister algebras, they're automatically normal. So this describes also the normal subgroups of the commutator subgroup and so on. And it proves the essential simplicity modulo the center in the simple case. So some of the theorems that in my previous slide are recovered here. All right, so now I want to move over to the algebraic setting. I'm not going to talk about closed normal subgroups, okay? And first, I start with a result, a very old result. So Herstein had asked the question whether a vector subspace of an algebra that is invariant under similarity had to be LDADL. We saw the definition. And then Amitsur give a counterexample. Okay? So it is not true that in a simple unit algebra, similarity invariant vector subspace must be LDADL. However, for simple unital sister algebras, turns out it is true. So again, this uses some tricks with functional calculus. So I don't know exactly how it would generalize. If I have a simple unital sister algebra, and I have a vector subspace that is invariant under conjugation. And in fact, I want to use for my applications invariant under conjugation by invertibles in the commutator subgroup. It's a small technical thing. Then it's either contained in the center, which certainly any subspace of the center itself, will be invariant under conjugation and it's a LDADL. Or the other extreme, it contains the commutators. It contains the linear span of the commutators. And of course, in either situation, either containing the center or containing the commutators, we verify it is a LDADL. So if you contain all of the commutators, you in particular contain the commutators of yourself with something else. So containing all the commutators automatically makes it a LDADL. So yeah, so the question of Herstein is true for simple unital sister algebra. Here, dropping unit doesn't help. Dropping simplicity, it's an open question in general. I'll come back to that question. So multiplicative theorem. So it turns out that in general, the invertibles are easier to handle than the unitaries with the methods that I am using. So I state first the case of invertibles. So let A be a simple unital sister algebra, and I take a subgroup of the invertibles connected to the unit. And let's say it sticks out of the center. It has at least one non-central element. Then, and it's invariant under conjugation by the commutator subgroup. Then it contains the commutator. In particular, the commutator subgroup is essential modulo its center. Okay, so once you divide by the center and you choose H inside of the commutator subgroup, then you get this so-called essential simplicity theorem. So it is true for any simple unital system. I gave a theorem that describes all the closed normal subgroups. In the case that these things are non-closed, I don't take norm closure here. I do need to assume things like simple or unital, you know, then this hypothesis now. All right, so so I want to start with a question that I credit to Marcoux. It's the source where I learned it. It basically is the same question that Herstein asked, but in the context of sister algebras and where the invariance is by unitaries. Let's take them in the connected component of the identity or not. I mean, it's not clear how that matters. Okay. I don't know how that happened. So there's a question? What?
Not that I see. Someone.
Oh, okay. So there are some stuff showing up in my screen. I don't know. Okay. So the question of Marcoux is, if you have a vector subspace that is invariant under conjugation by unitaries, is it the Lie ideal? Okay. So the theorem that is now a new theorem is that if you for simple unital sister algebras, yes. So is that something that
I don't know. Can we tell who's doing? Whoever is touching the screen, could they please sort of refrain from that? Thank you.
Oh yes. How did that happen? Oh, I see. Okay. So okay. So the theorem is then that that Marcoux's question is has a positive answer for simple unital sister algebras. So if I have a vector subspace that is not contained in the center and is invariant under conjugation, and in fact, for our applications, we want the unitaries to really understand the simplicity of the commutator subgroup. We want invariant under conjugation by commutator unitaries. Then again, you have this alternative: either it's contained in the center or contains all the commutators. So in this case, I stated it as if it's not contained in the center, then it contains the commutators. In particular, it will be a Lie ideal automatically. Okay, so moving over to the multiplicative theorem. Unfortunately, there is a technicality here in the handling of the passage from one theorem to the other, and where I need another technical assumption. And in this case, there's options for what you can do. But in this theorem, the technical assumption is the existence of a non-trivial projection. So if there exists a non-trivial projection in a simple unital sister algebra, and if I have a subgroup of the unitary group that is not invariant under conjugation by commutator unitaries, then again, it either contains all the commutators or is contained in the center, or the way I stated it here, it's either non-central. If it is non-central, then it contains. So under these conditions, again, we prove essential simplicity of the commutator subgroup. Okay. Okay, so with Abhinav Chand, we've been revising this a little bit. And so I mentioned here a couple of these technical assumptions that we need to make this passage from the additive to the multiplicative setting. So A is a simple unital sister algebra. And suppose that either A contains a projection that is neither 0 or 1, or I can embed a dimension drop sister algebra into A. And in particular, I mean, if you don't know the definition of this, well, at least you may have heard of the Jiangsu sister algebra. So if this so-called Jiangsu sister algebra embeds, and basically what these conditions are doing are ensuring some sort of matrix-like structure, okay, to do some arguments. And now let's say I have a subset of the commutator subgroup that is invariant under conjugation, and that generates the group. Then there exists generates it just as a group. It's a generating set. Then there's a power of the set, so products of elements of X, such that we will contain this specific generating set, exponentials of self-adjoint commutators. And I could also put here those square zero elements. So basically, any generating set that is invariant under unitary conjugation after you raise it to a finite power, will contain this sort of canonical generating sets. Okay, so this it improves the previous theorem in that well, it doesn't really improve it, I guess, but let me see. Yeah. Yeah, instead of a generating set, we could have written any non-central, any set that is not contained in the center, which would automatically be a generating set by the essential simplicity. Okay, since it's invariant under unitary conjugation. So basically a conjugacy class. So let me put it this way: if X is the conjugacy class of a non-central element, then there's a power of that conjugacy class that contains all the exponentials. All right, so then so there are some wrinkles there to iron in what I have presented, removing that technical assumption, answering a number of questions. However, we have moved on to look at other properties of the commutator subgroup around simplicity, but that come together with the so-called regularity properties of sister algebras. So what do these regularity properties of sister algebras give us extra, you know, besides this simplicity property? And so there's a concept out there called bounded normal generation. So which it's a strengthens simplicity. So let's say G is a simple group, and then we say that it has bounded normal generation. If for every element other than the unit, if I look at its conjugacy class and the conjugacy class of its inverse, then there's a finite power of that, meaning finite products of things taken from that set, that gives me the whole set, the whole group. So yeah, so this it's automatically implies simplicity of G, but the point here is that instead of taking the union of the powers of the conjugacy class of G and G inverse through all the natural numbers, we can stop at the finite number. After a finite number, we generate the whole set. So the work on factors was done by Dower and Tom. And basically, they show that if we have one of these simple factors, you know, 2, 1 or type 3 factor, then in this case, we don't have to talk about connected component identity. We don't have to talk about commutators, you know, just directly the unitary group. And S1 here, by that I mean the center. So the center of the unitary group has bounded normal generation. So this improves. And I should point out that this is also true for finite factors. So, I mean for type 1 n factors, okay? And that's more, it was classically known, but I don't know the reference for that, but it was known that the projective special unitary groups are simple. And I'm not sure whether the bounded normal generation was in the literature, but it is true too, and Dower and Thom also prove it in that case. Okay. So we have taken up this and now move over to the sister algebra setting and see what we get. So okay, so the theorem that Abhinav Chand and I have says that if we have a simple purely infinite sister algebra, then again, because the sister algebra has no bounded traces, the commutator subgroup agrees with the whole unitary group. So in this case, I only talk about the whole unitary group. And again, well, the center, I denote here by S1. And basically, we again observe bounded normal generation in the simple purely infinite Now, let me discuss a little bit the relaxation of the hypothesis of that theorem. So, so it turns out that in the case without bounded traces, regularity, so-called regularity properties do not enter so much. This will, and this we do know now, we do believe are relevant in the case with traces. But here are the hypotheses that really needed to make that theorem work. On one hand, you need a unital sister algebra without bounded traces. Then you want the existence of a projection that is full. So notice I drop simplicity. There exists a projection P such that both P and 1 minus P are full, meaning they both generate the algebra as a closed two-sided ideal. Okay, and this is a technical condition one expects to be able to remove, but you may remember it from before. So then let's assume also that we have finite exponential length. So in the case of a simple purely infinite sister algebra, we have real rank 0. So we do have this finite exponential length. The finite exponential length is necessary for bounded normal generation. And if we are talking about commutator subgroup, then what is necessary is finite commutator exponential length, so-called. So this is a necessary hypothesis. Finally, I need to take an element G that is non-central, but I wanted to, in no quotient, does this unitary become central? That's basically the last hypothesis. Okay, so which is another way to put it is that its set of commutators with the whole algebra is a full set. Okay, so in no quotient G becomes central. Then again, the conjugacy class of G and G inverse after a finite power. So you have a sort of bounded normal generation on those elements, and we can apply this then to B of H, I guess. Okay, all right. So, okay, so this is my last slide. So I'll go over the work that I'm doing right now and a number of questions. So first, I mentioned I'm being somewhat cautious here in that we sort of have a proof for C-stable algebras, but there are a number of details that need to be checked. So I will just not quite state it, but the expectation is that if I have a simple unital C-stable algebra, so then I can assume it's either purely infinite or has stable rank 1 by Rotterdam's dichotomy. And we have already dealt with the purely infinite case. So the case that remains is the stable rank 1 case. And then again, we expect to find this sort of bounded normal generation. Okay, so I need to assume finite exponential rank as well. This is necessary. Okay, now it may be the case that all C-stable simple unital sister algebras have finite exponential rank. It may be that this follows from the classification, from the new approaches to classification. Okay, so the next question is, if I look at the square zero elements, I just want to advertise this question because it's a very simple question. Is this linear span of the square zero elements? No, forget that whether my previous question, whether it agrees with all the with the linear span of the commutators. Is this a Lie ideal? So if I take a square zero element and I take its commutator with an arbitrary element, is that a linear combination of square zero elements? And I guess it's unpublished counterexample by George Bergman for an arbitrary algebra. So it's possible so it's not true for arbitrary algebras. But other than that example, I don't know. So so of course, I do believe that this bounded normal generation is a manifestation of regularity. So I do expect that there exists simple unital sister algebras for which this projective unitary group. So the commutator of the unitaries divided by the center. Sorry, I always mean the connected component of the unitaries. Does not have bounded normal generation. So one would expect that Villotsen's techniques can be adapted, but remains to be seen. And another question that did occupy me a little bit, but it seems a little tricky, is when, so that's why I asked, when does the commutator subgroup have the Bergman property? So what is the Bergman property? It basically is somewhat similar to something I put in a slide back there. So you think you almost have it. So it basically says that any generating set doesn't have to be invariant under conjugation. Any generating set, your group has finite diameter. So anything is a finite word on a generating set. So Bergman proved this for the infinite symmetric group, and Doward proved it for the unitary group of type 2, 1 and type 3 factors. So, so it's natural to act that for sister algebras as well, and but there are some technicalities there where it's not so clear to me. I will show you before I stop my slide from a while back here, where there is something like, oh, this one here. So here we have a generating set, and a finite power of it contains this specific generating set. Now, if we know something like finite exponential length, then from here we can get all unitaries. But the main problem with this, our theorem here, is that the set X is invariant under conjugation. That's a very small collection of generating sets compared to as one has in the Bergman property. So and that's it. Thank you.